In section 5.4, we're going to talk about equations that involve exponents or logs, and both of them kind of have some of the same properties. So let's start talking about exponential equations. And what we're going to be doing is expressing each side of this equation as a power of the same base. In other words, when we have something raised to an exponent on both sides, if that number, b, the base, is the same, then it makes sense that the exponents would have to be equivalent. So what we're going to be able to do is if we can get it to the same base, then we can write the exponents equal to each other, and we can solve for the variable that's in the exponents. Now, the reason we're doing this, of course, is because we have a variable, an unknown, in the exponent, and we have to be able to solve for it. So let's take a look at this first one, this first example we've got, which says e to the power of 3x plus 9 is equal to e to the power of 6x minus 3. And what you notice first is that it's two exponents. It's an exponential equation, and the bases are the same. And this one's an easy one. All we have to do is take the exponents and set them equal to each other. There's only one unknown. It's x. So we now solve for x. Now I'm just going to take this 3x to the other side because I've got more x's over here. So I'll subtract 3x over here and subtract 3x from 6x. I get 3x. So I'm going to add 3 to both sides. And when I add 3 to 9, I'm going to have 12. And what you see I have is 3x is equal to 12. Divide both sides by 3, and x is equal to 4. So I have solved it just by setting the exponents equal to each other. And it's a simple equation. Now this one gets a little more complicated. Of course, it can't all be that easy. Let's take a look at this one. This one is 32 raised to the power of x plus 2, and the other side is 2 raised to the power of 7x plus 12. Well, they're not the same base. But if we can get them to the same base, then we can follow this procedure, and it's a simple solution. So we look at it and say, well, we're not going to get 2 to any other base. We can't get 2 to base 32, but could we get 32 to be base 2? And what I think about is this. 32 is equal to 2 to what power? What can I raise 2 to and get 32? Well, I know 2 raised to the power of 3, or 2 cubed is 8, and then 2 squared is 4, and 4 times 8 gives me 32. So if I think about it, I go into my calculator and I say, okay, 2 to the power of 5 maybe? Let's check it. So I'll go 2 to the power of 5, and that is 32. So I'm going to say 32 is equal to 2 to the power of 5. That's what I'm thinking. I'm putting it over here in brackets to go. That's what I have to think about. So now I'm going to change this 32 right here to be 2 to the power of 5. And then I'm going to multiply that 5 times whatever I had in the exponent, x plus 2. What's this equal to? It's 2 to the power of 7x plus 12. And now I have the same base. So all I have to do is set these exponents equal to each other. So I can say 5 times x plus 2 is equal to 7x plus 12. Well, that's pretty simple. I'll distribute this 5, and I get 5x plus 10 is equal to 7x plus 12. Now, I want to work on the side. I usually start with the side that has a smaller variable, so I'm going to subtract 5x from both sides. I would end up with 2x. Since I've got the x's over here, I'm going to subtract 12 from both sides, and I'll say 10 minus 12. That gives me a negative 2. And then when I divide both sides by 2, I find that x is equal to a negative 1. That's my solution. What about this next one? This one is an even worse problem for us because it's got a fraction, and it's 1 over 81. Now the base of this exponent is 3. 3 to the, we don't really care what the exponent is, it's just 3 to raise to a power. Can I get this 1 over 81 to be something 3 raised to a certain power? Well, if I think about it, I think about 81 is actually 3, and I know this one because I know 9 times 9 is 81. And I know 3 times 3 is 9, so I'd actually have 4 3's multiplied together. 81 should be 3 to the power of 4, but I'm not going to take my word for it. I'm going to go 3 to the power of 4, and I'm going to check it. Okay, so that did come out to be 81. So I know 81 is 3 to the power of 4. What's 1 over 81? Well, 1 over 81 would be 1 over 3 to the power of 4, wouldn't it? Now, how would I get that to be in the numerator? Well, then I would say this is really equal to 3 to the power of -4. That's my thought processes that I have to go through to get this to base 3. So all I have to do is change that 1/81 to 3 to the power of -4. And I have equivalent. I have the bases are the same bases, like bases. So this is going to equal 3 to the -4. And now I've got the same base. All I have to do is set these exponents equal to each other. X squared plus 4x is equal to a -4. Now, this is going to be quadratic. I know that because I've got x squared. So I'm going to go ahead and get everything over to this side because that's where my positive squared, x squared is. And when I do that, I'll add 4 to both sides. And then I have it equal to 0. And now all I have to do is factor it. And isn't this a perfect square trinomial? So what I'm going to do is say, I know both of these operations have to be plus. I know I would factor the x squared into x times x, and the factors of this, the square root of 4 is 2. And check it, this would be 2x plus 2x, that would give me the 4x in the center. So I really have x plus 2 times x plus 2 is equal to 0. So what is x? Well, they're both the same thing, so all I have to do is set 1x plus 2 equal to 0 and solve for it. I mean, they would both be the same thing. They would both tell me that x was -2. So I just have one answer, and it's x is equal to -2. Now, on page 25, we're going to look at what happens when we simply cannot get both sides to the same base. And we're going to use logarithms to solve these. So I'm going to make a note here that says, use this when you can't get both sides to the same base. All right, so how do we do that? Well, then we're going to simplify it. We're going to use either the common log or we're going to use the natural log. Take the natural log of both sides or the common log of both sides. How do you make a decision? Well, it's going to be determined by what your numbers, your equation looks like. If it already has an e in it, then we'll use the natural log. If it has a base 10, we're going to use the common log. And basically, we'll probably use the natural log for anything that doesn't have a base 10, basically, is what we'll do. So those instructions are up there in case you forget that. Let's take a look at this. And it says we have 2 to the power of x is equal to 38. Now, we've got a choice about which log to use. It simply doesn't matter if you use the natural log or the common log. And I worked this one using the log base 10. So I used the common log for both of them. But what I found was that I couldn't change 38 into 2 to the power of anything. I mean, 2 to the power of 5 is 32, and if I go up 1, I'm going to go way past 38 when I have 2 to the power of 6. So I've tried everything, and I can't get that to be 2 to the power of anything. So I know I've got to do logs. And what I did first was I said, so take the log of both sides. And I'm going to use the common log, like I said, log of 2 to the power of x. I said that was equal to log of 38. So I just basically did the same thing to both sides. I took the log of both sides. And remember, this is base 10. If we don't write it, it's understood that that's base 10. That's the common log. Now, I've got an exponent over here. And so I'm going to be able to bring that exponent out front. And I do get my x variable out of the exponent by doing that. So I'm going to say x times log of 2 is equal to log of 38. Now, the next thing I'm going to do is say, well, I want to get the exponent all by itself. So what I'd have to do is divide it by log of 2. I'll have to do that to both sides. So when I finish that, I have x all by itself is equal to, and here's the exact answer, log 38 divided by log 2. Now, this would be what we call, if they ask for the exact answer, this is it, expressed as the 2 logs. But you know that you can take your calculator and figure out what those are. So I can say in my calculator, I can go, I want log, and I'm going to use the log button, see if I can get it so you can see it. I'm going to say log 38. And then I'm going to say divided by log of 2. And I came up with an approximate answer. Now I'll go to 2 decimal places and call that 5.25. But I know that that is not an exact answer. It is the approximate, it's the decimal approximation. So you give your answer in whatever form it's asked for. Decimal approximation or the exact answer does involve the logs. All right, let's look at another one. This one is 10 to the power of 10 plus 2, and it's equal to 75. And because that is a base 10, and I can't get this to a base 10, but this is a base 10, so I'm definitely going to use log for this one because my common log is a base 10 log, and that'll help me, as you'll see in our equation in just a minute. So I'm going to just make a note. I'm going to definitely use the log base 10 since this is we have a 10 in it, okay? We have a 10 as one of the bases. And I'll come over here and say, well, I want to take the log of both sides. So I say log of 10 to the x plus 2 is equal to log of 75. Now I get to bring my exponent out front now because of the rules of the logs and how we can redo that. I'm going to say x plus 2 times log of 10 is equal to log of 75. Now, something neat has happened in this one. This is log base 10 of 10. And remember what happens when we have the same base. Remember, this is an unwritten base here. We have the same base that we have the argument of the log. When we do that, this thing is the number 1. That's all it is. So I can say, well, I can replace that with a 1. So all I have on this side is x plus 2. And that's equal to log of 75. And, I'm sorry, that's kind of looking like an arrow. And I'm going to say, and it looks like a 1/2 now, so I'm going to just kind of move it over here. And I'm going to say, I need to now subtract 2 from both sides, don't I? So when I say x, I would say minus 2 over here, I have just x. And now I'm going to say log of 75 minus 2. And there's my exact answer. The answer for x is equal to log base 10, or the common log 75 minus 2. Now, if I want to get the decimal approximation, I put it into my calculator, and I say I want log of 75 minus 2. And that would be my approximate answer here. Approximately negative 0.1249 will go to 4 significant digits. Most of the time you're going to be asked for this format, okay? Let's do one more here on this page. If I have e raised to a power, I'm going to use the natural log. I'm going to use the ln log, and that's because I had a base e. Okay, so that exponent has a base e. I'm going to use the natural log. But first, I've got some other stuff to do. This term with the exponent has a minus 11. Let's get rid of that. Let's add 11 to both sides. I would have 2 times e to the 4x plus 1. Now, I added 11, so I'll add 11 over here, and this becomes 26. Write it down if you need to. A lot of times you can say it to yourself, and as long as you're saying it to yourself and you're getting it right, you're okay. Now, I have a coefficient, and I have a coefficient that I can divide. So I'm going to divide this side by 2. I'll divide that side by 2. So this ends up being e to the 4x plus 1, and that's going to equal 13. Now what do I do? Well, now what I can do is I can just take the natural log of both sides. So I'm going to come over here and say I want the natural log, and you can write it in cursive if you want to. I'm going to sort of separate it so that I have it. It's the natural log of e to the 4x plus 1. I should have written that a little bit lower. And that's going to equal the natural log of 13. Okay, so what is this? Well, remember, the natural log is really log e, log base e. So what we've got here is log base e of e, right? What is log base e of e? It's really 1. So this is going to be 1 to that exponent, isn't it? Now that gets a little bit tricky. So what we're going to do first is we're going to bring our exponent out front. We're going to say 4x plus 1 times the natural log of e. And that's equal to the natural log of 13. I decided my L's were looking like 1s too much. All right, what happens here? This is log base e of e, and it is the number 1. Okay, so I have 4x plus 1 is equal to the natural log of 13. And now I just need to get this x isolated. So I will subtract 1 from both sides. I'll move over here and say this is going to be 4x. I subtracted 1, so I'm going to have the natural log of 13 minus 1. And then the next thing that's going to happen is I'm going to divide this by 4. So I'm going to have x is equal to the natural log of 13 minus 1 divided by 4. And that would be my exact answer. Plugging it into my calculator would give me my decimal approximation. So let's see what I get. I'm going to say ln of 13, and then I'll say minus 1. Now, if at this point I say divided by 4, it'll take the 1 and divide it by 4. I would have to put this whole thing in parentheses before the log and after the 1, and then say divided by 4. Or I can do this. I can hit enter and let it get that answer, and then say divided by 4, and it'll divide this answer by 4. And I end up getting x is equal to, or approximately equal to, 0.39. Let's be careful with those, because you know your calculator does understand order of operations very well. Now, we're going to take the definition of a logarithm and use it to help us solve some of these equations. Now, what you have to remember is that really logs are just exponents. Log base b of m equals c means that b to the power of c is equal to m. Remember how we could translate from log formation to the exponential formation of our equations. So all we have to do is put these in the correct format sometimes, or do this translation, and it makes it a lot easier for us to solve. Now let's take a look at this first one that's already written in the log format, and it's really the natural log of x is equal to 3. But to be able to write that in exponential form is not quite easy until you remember this part. This is really log base e of x equals 3. So the base is e. If I say e to the power of 3, then I can say that's what equals x. And remember how we did that. Now, we have e on our calculator, so we can say e to the power of 3 because that's the answer for us right there. And I'm going to come in here, and I'm going to find e, which is above the division button right here. And I'm going to say second and hit that division button and insert e. And then I'm going to say raised to the power of 3. And then as I hit enter, I see that e cubed, e to the power of 3, is 20.09 approximately, right? So I'm going to say x here is approximately equal to 20.09. Now, if it bothers you to write the x variable on the right, then turn it around and write it on the other side, okay? Now, how would I we check most of these, but we check when we're using any of the log properties. This one, you would always check them for one thing. You would check to see that when you put this answer back in, it didn't create a negative logarithm. You weren't trying to find the log of a negative number because that makes it invalid. But this one is not going to be the case. I'm not really going to have to check it. But I do want to note one thing with you. If I said the natural log of 20.09 and entered that, I would get my 3 back, or really, really close, right? Because I used a decimal approximation there. So if I use my calculator, I can check it. when I plug in the natural log of 20.09, I say, yep, that is equal to 3, or really, really close to 3. Now let's try a few more of those. I've already got them in log format. I'm going to change them over and switch them to exponential format to see if they're easy for me to solve, because I've only got the log on one side here, right? So I'm going to say this is 2 to the power of 5, and that's going to equal 8x. I'm just going to use my circular format to show me that, to help me put it in exponential format. So when I write it, I'll say 2 to the power of 5 is equal to 8x. Now, to solve that, I need to know what 2 to the power of 5 is. And so you'd take it and put it in your calculator if you didn't know, and you'd find out it's 32. And now we just have to divide both sides by 8, and we find out that our x is equal to 4. So that was fairly simple. Let's look at the next one. This one, we've got log base 10, don't we? It's not written, it's base 10. So this is 10 to the power of 2 is equal to, and this is the argument of the log, what's inside parentheses. So I'm going to say 10 to the power of 2 is equal to 13x plus 9. Now 10 squared is 100. And that would be 13x plus 9. Nothing much I can do over there. I do want to subtract 9 from both sides. And when I do, I end up with a 91 over here, don't I? Is equal to 13x. And then I want to divide both sides by 13. So that one, maybe they divide evenly. Let's see. 19 divided by 13. They do. It comes out to be 7. So I'm going to say x is equal to 7. So that was not very hard. Now let's look at the third one. The third one has a point that I need to make with you, something that you might want to put 3 stars by to help you remember. This one, before we can do this and change it to exponential format, we must have a leading coefficient equal to 1. In other words, we have to divide both sides by 2 before we can do this, okay? So I'm going to divide this side by 2, and I'll divide this side by 2, and I end up with log base 4 of x squared is equal to 3/2. Okay, it's not as pretty as I like, but that's okay. I couldn't do it with the 2 out there. So now I'm going to say 4 raised to the power of 3/2 is equal to x squared. So I'll say 4 to the power of 3/2 is equal to x squared. And I've really kind of got to think about what 4 to the power of 3/2 is. So I'm going to come over here and draw it out. Here's my thought process. This is really the square root of 4 cubed. Okay, remember how to write that as a radical? So this is going to be, under the radical sign, I'm going to put 4. Now I could cube it outside, or I could cube it inside. I mean, it really doesn't matter. How about if I just do the cube on the outside? I could put 4 cubed under there, and then I would say 4 cubed is 64, and the square root of 64 is 8. But what if I do it this way? And I come up with, let me just go down here, and I come up with the square root of 4 is 2, and 2 cubed is 8. Both ways it comes out the same thing. So you can put the exponent under the radical, or you can put it outside and resolve the radical first. Either way, it's really whatever makes your math easier. So what did I find out? Well, I found out that this 4 to the power of 3/2 was really equal to 8. So I'm going to come over here and say 8 is equal to x squared. So how do I find x? Well, I take the square root of both sides, don't I? And that's not a perfect square, but I'm going to say x is equal to, and I have to say plus or minus the square root of 8, right? Now, that's good enough, really. I mean, I would probably simplify that a little bit more and take out the perfect square we see inside it. But for what I want to show you right now, it's probably best left alone here. What we have to do is go back and see if it will cause a negative log in here. Now, when I say 8, if I insert the square root of 8 for x squared, I'm really going to say that's 2 times the log of 4, and it would be the positive square root of 8 squared, right, which is just going to be 8. And so that one checks out because it's the positive it's the positive, it's taking the log of a positive number. And I can do that. Let's try the negative square root of 8. So this is 2 times the log base 4. And under here, I'm going to say this is negative the square root of 8 squared. Well, when I square the negative, it becomes positive, doesn't it? So it is also just going to be 8, isn't it? It's going to be the square root squared is just going to be 8 because I squared the negative too. Okay, so that's fine. And both of these will work. So I've checked them. And I do have to check anytime I'm using log properties of logs. I have to check to make sure I haven't caused the log of a negative number. If I ever find that there's a log of a negative number when I go back to my equation, I don't have to do anything else. I just say that is not one of the solutions. Now let's talk about a property of logs that's going to be sort of similar to what we did with exponents when in the exponential equations we solved. This one's called the one-to-one property of logs. Now that means that if we have a log with the same base on both sides of an equation, and remember these both have to have a coefficient of 1, okay? They can't have, like, one can't be 2 times and the other one 3 times. They can't have coefficients that are not 1 out there, leading coefficients. So, but if the base is the same, the coefficients are 1, then these arguments right here can be set equal to each other. We can get rid of the log completely. Now this is one of those properties of logs that once you use it, you got to check your solution because you'll come up with extraneous solutions a lot of times when you're doing this. What you have to do is put it back in and make sure that you're not causing a log of a negative number in any place that there's a log in the original equation. So let's see if I can look at this first one. And it says log base 4 of 2x minus 3 is equal to log base 4 of 9 minus x. And these are both the same log base coefficients of 1. So this is simple. All I do is say 2x minus 3 is equal to 9 minus x. And I'm going to solve that by getting the x's to the same side. That's a negative x. What if I add x here and I add x here? I'll end up with 3x. And then I'm going to add 3. So when I add 3 to this other side, it'll be 9 plus 3, and that's 12. Divide both sides by 3, and I have 12 divided by 3, which is 4. And now I'm going to have to go back and check it and make sure I didn't cause either one of these logs to be negative. So I'm going to check it. And what I'm checking is the answer, x equals 4. Now, sometimes you'll have multiple answers to check, so it's a good idea to write down what you're checking. So this one, I'll plug it into the first log. Log base 4 of 2 times 4 minus 3. Now, does that cause this to be a negative number? Well, that's 8 minus 3, which is 5. This one's okay. Let's check the other log. Log base 4 of 9 minus 4. And that also came out to be 5, which is a positive number. So it checks. So this one does check. It's okay. And you're going to have to prove on your test that you have checked these if you use the properties of logs. Now let's look at this one. It says we've got the natural log of x plus the natural log of x minus 5, and that's equal to 2 times the natural log of 6. Well, at first it looks like it's a little more complicated than we want it to be, but then I remember one of my properties of logs says that if I have 2 logs that are the same base and they're added together, then I can take their arguments and I can multiply them. So let's see if I can simplify it a little bit by doing that, and that way I wouldn't have 2 logs on this left side. So I'll say the natural log. This is really the same as the natural log of x times, and I should have used a different bracket, times x minus 5. I'm just multiplying the log arguments together. Because they're added, that means the same as multiplication. And I'm not going to do anything over here to this side. Just the 2 times the natural log of 6. Now, the other thing I could have done, I have to get rid of that 2, don't I? So can't I take it to the other side of the log and make it an exponent? So if I do that, what I've got is the natural log of 6 squared, okay? And that becomes a coefficient of 1. So now I have natural log of an argument, natural log of an argument. I can set the 2 arguments equal to each other, and I'm done. Or I have to solve, but I'm pretty much done with the logs anyway. and this is going to equal 6 squared. Okay, that's pretty good. Let's go ahead and distribute this. X times x and x times negative 5. And over here I've got 36. Now this is going to end up being a quadratic because I do have x squared. So let's get everything over to this side and see what happens. X squared minus 5x, and I'll subtract 36. And that's going to equal 0. And now hopefully it'll factor, right? Let's try it. And it would be one of each sign, so I'll put 1 plus 1 minus. There's my x times x. I want factors of 36 that subtract from each other to give me 5. And it looks like I can think 9 and 4 will do it. It would have to be a negative 9 and a positive 4. So those are my two factors. So when I look at that, what are my values for x? Well, you think about it this way. I'm going to set x plus 4 equal to 0. And I'm going to set x minus 9 equal to 0 and solve. And most of the time you guys are doing this in your head now. Just make sure you get the signs right. And I've got two values. I've got to check them both. Now I'm going to go up here and say negative 4. If I check negative 4, I'm going to check the first one as x is equal to negative 4. When I put ln of negative 4, I have the log of a negative number. It doesn't work. So I can come over here and say that is not going to be one of my solutions because I can't take the log of a negative number. So that took care of that one. Let's try 9, okay? I have 9 here. Natural log of 9, I'll go ahead and write it down. Natural log of 9 is okay. That one's okay. What about this one right here? This is the natural log of 9 minus 5. Well, that's not going to be a negative, so I'm okay with that. And this is 2 times the natural log of 6. There's no variable in there. There's nothing to put, there's nowhere to put my x is there because there's no x on that side. So all I had to do was check these two. But that means x minus 9 checked, and it is my solution. X is equal to 9, rather. Now let's take a look at this one. This third one says log x, and it's log base 10, remember, minus log base 10 of x plus 3 is equal to a negative log base 10 of x minus 1. Well, fortunately, they're all base 10s, aren't they? Now, I've got two logs over here. Since they're subtracted, remember what we can do to them to make it a single log. I can put this as a fraction, x over x plus 3. That's what subtracting the logs does for me, okay? Now, what do I do over here? Well, over here, I'm going to say this is really, I want to get this negative 1 to go to the other side. This negative 1, I've got to get rid of it. So I'm going to say this is really log of x minus 1 raised to the power of negative 1. I don't really like that, but that's okay, isn't it? Now, what would that look like? Well, it would look like a fraction. It would have a numerator of 1 and a denominator of x minus 1. Now, when I find this, though, I've got log base 10, log base 10. I can get rid of the logs, can't I? So what do I have? I have x over x plus 3. And I'm going to go ahead and write this as a fraction. It's really 1 over x minus 1. Okay? Now, how do you solve an equation that has fractions? Well, you multiply through every term in the equation by the common denominator. Least common denominator for this one is both of these binomials, isn't it? So I'm going to write it out. Least common denominator is equal to x plus 3 times x minus 1. And I'm going to multiply this side times that x plus 3 times x minus 1, right? So I'll say this is going to be times x plus 3 times x minus 1. And when I do that, that's over the number 1, right? And when I do that, I notice that the x plus 3's cancel out. And all I have to do is say this is really x times x minus 1. Let's do the same thing over here. Times x plus 3 times x minus 1. And this time the x minus 1's cancel. And I'm just going to have 1 times x plus 3. Okay, that's not bad. X times x is x squared. X times negative 1 is negative x. And this is equal to x plus 3. I've got another quadratic, don't I? Let's get everything over here to this side. I'll subtract an x. I have just nothing, no x squares to combine. So I've got to subtract an x. I'm going to have, this is going to be minus 2x, isn't it? And then I'm going to subtract 3. And now finally, this side's 0. Write those steps out that I am doing verbally for you. If you need to, you would just say minus x, minus 3, and you would go minus x, minus 3, and make sure you know what you're doing, okay? Now, I've just got this quadratic that I want to see if I can factor here. So I'm going to come down and say I need one that's x plus and one that's x minus. Factors of 3 that will subtract to give me 2, and the only factors of 3 there are 3 and 1. So if I said negative 3 plus 1, I would get a negative 2, wouldn't I? So those are going to be my factors. And x, therefore, is going to equal a negative 1 and a positive 3. Now, I'm not writing those out. X plus 1 equals 0, x minus 3 equals 0, and solving. Make sure if you do it the way I'm doing it that you get the signs right, okay? But I think you're probably to that point. Now, we do have to do some checking. So I'm going to say check, and the first one I'll check is x is equal to a negative 1. Now, x is a negative. That's okay. It's okay if the answer is a negative so long as it doesn't cause a negative log. But when I go over here and I look to see if it causes a negative log, the first thing I see is log of x. And I can't do that, right? So that one is out. So I can say, okay, let's check x is equal to 3. And the first log I check is log of x. Well, that would be log of 3. That's okay. This one is going to be log of 3 plus 3. Well, log of 6 is okay. And this one, now it doesn't matter if that log is negative out front. We don't care. Negative log, I'll put negative log of 3 minus 1. This is the part we care, if this part is negative or not. 3 minus 1 is 2. That's positive. So this is okay. So the answer I have for this one is the negative 1 didn't work, but x is equal to 3 does work. Now, I don't know if you remember, but back in section 5.1, I think it is, there's a page that I took out because it didn't belong there. It belonged here. So I'm going to give you a couple of problems using the interest formulas, the exponential equations that we have. And the first one I want you to write down is this one. Remember, this is the continuous interest, continuing interest, compounded continuously rather, and it's the amount is equal to the principal times e to the power of RT. All right, so I'm going to say, what if I started with a base amount of 6630, and then, I'm sorry, that was the ending amount was 6630 after interest was compounded, and the base amount I'm starting with, what I started with, the principal I start with is 5578, and then it was compounded continuously over 10 years. The only thing that you're not given is this rate. And this rate is in the exponent. Now before, where it was inserted in your pages incorrectly, we didn't know how to solve for an unknown in the exponent, but now we do. So let's do this one just for practice. And let's say I'm filling in, this is the amount that I ended up with, 6630 after interest, and then I started out with 5578. And then I'm going to say that's times e to the r is unknown, but t is 10. I have everything here given to me except r, the rate. And so I've been asked to solve for what the rate is. What is the rate of interest for this particular scenario? So now that I know how to do it, the first thing I do is I say, well, I can't do much as long as I don't have a coefficient of 1 in front of this exponent. So I'm going to divide both sides by 5578. That'll take care of that. Now these numbers are not going to be pretty. And they never are when we're dealing with these types of problems. So you just kind of get used to it. So I'm going to say 6630 divided by 5578. And I'm going to take it to 4 digits after the decimal place, perhaps. Well, let's see. Let's just do 2 for this one, just for argument's sake. And this one becomes 1, doesn't it? But over here I've got 1 point, and I'll round to 2, 19. And that is equal to e to the power of 10r, right? I mean, I could rewrite that. It would be better as 10r than r times 10. And now what can I do? Well, now I can take the log of both sides. That's how I would solve it. And since it's e, I'm going to take the natural log, right? So I'm going to take the natural log of 1.19, and that's going to equal the natural log of e to the power of 10r. Now, when I do this, I'm going to be able to come over here and say, well, this would come out in front, wouldn't it? Let's just go ahead and write that down for you. Over here, this exponent would come out in front, and it would be 10r times the natural log of e, which we know that that natural log of e is equal to the number 1, because it's really log base e of e, and that is equal to the number 1, right? So I'm really just going to be able to say, okay, natural log of e, I just use the exponent. There's my shortcut, okay, if you want to if you just want to memorize that. So now I've only got the log on one side, don't I? And all I have to do is say, well, how would I solve this? Well, I would simply take it and divide both sides by 10. So r would be the natural log of 1.19, and it would be divided by 10. Okay, and that's not too bad to type into my calculator as it is. And that's the exact answer, but let's see what the natural log of 1.19, close up parentheses and say divided by 10, and I get 0.01739. Now, what we're usually told is to go to 4 significant digits. Now, that 0 past the decimal is not significant. The first non-zero that we hit past the decimal is where we start counting. So I'm going to use the 1, the 7, the 3, and I'd have to round that 9 up, wouldn't I? So it's going to have to go up to a 10. That would make it a 1740. So the rate is going to equal 0.01740. These are the 4 significant digits that I was told to round to, okay? So that's just something else to keep in mind. Now, that does look like the appropriate rate for that particular formula. Now, let's take a look at another one. Now, I want to do one that's got the other formula in it, which was the interest that was compounded. Let's do this one daily, okay? So we're going to say compounded daily, and the ending amount they've given us was $25,875. And the principal that they started with was $11,250. And the rate is given to us. It was 0.044. And n, the number, it was compounded daily, so n is equal to 365. That's all I have to have, besides the formula, which was a is equal to p times 1 plus r divided by n, and it's raised to the power of n times t. Okay, the only thing we don't have this time is how many years. How many years did it take for this amount of principal to become that amount of money if we have a rate of 0.044 and it's compounded daily? This is how I would find out. Now, the first thing I want to do is fill in the blanks. I've got amount is equal to $25,875, and that's equal to the principal of $11,250. And that's multiplied times 1 plus, and the rate was 0.044, and it was divided by 365, raised to the power of 365 times t. And there's the unknown. What I'm trying to solve for is in the exponent. But first things first, let's get rid of this 11,250, okay? Let's divide, because it's multiplied times all that. Let's get rid of it by dividing both sides by that number. Here we come with some really unattractive numbers again, but here we're just used to it by now, right? 25,875, and it's divided by 11,250. And I checked to see, did I enter that correctly? And I've got 2.3. I didn't even have any repeating decimals there. So I've got 2.3. And that came out to be 1, of course. That's equal to 1 plus 0.044 over 365. And that has to be raised to the power of 365t. Okay, the next thing I'm going to do is see what I need to do to get that exponent down. Now, what I would pick is, it's not log base 10, but it doesn't matter. You can use the natural log or you can use log 10. And I usually, use whichever one you want to, and we'll go ahead and get rid of it, okay? We're going to get this decimal, what am I trying to say? This exponent to come to the front. But before we do any of that, why don't we take care of what's in these parentheses right here? Let's take care of what is 1 plus this incredibly busy fraction. So let's go ahead and do that. We'll say 1 plus, and I'm going to put in parentheses 0.044 divided by 365 and see what that comes out to be. Now, it's a very long repeating decimal, but we're going to make it a little bit simpler on ourselves this time. We're going to say this is 2.3 equal to 1.0001 raised to the power of 365t. We've got all of this. This is really just one number inside there, so there's no sense in us keeping it so busy. Let's go ahead and simplify it like that. Now, we've got the unknown in the exponent, so we're going to have to use logs to get it out, and we'll go ahead and say this is the log, and it doesn't matter if you used ln or log, but I'm just going to use log of 2.3, and it would be equal to the log of 1.0001 raised to the power of 365t. Now, I know that I can bring it to the front of this log to take care of it, so let's do that. So this is really log of 2.3, and that's going to equal 365t times, I'll put a times there, log of 1.0001. Now, certain things I can go ahead and resolve because I cannot divide this side by log of this 1.0001 because it has a coefficient that's not a 1. So I can't divide both sides by the same thing. So all really I can do is start resolving these logs. And I'm going to find out what the log of 2.3 is. And the log of 2.3, let's just make it easy and go to 4 decimals. It's 0.3617. And that's going to be 365t times, and what is this one? This is a log of an incredibly small number, so let's go a log of 1.0001. And I find that it says move the decimal 5 places in the negative direction. So what it's going to be over here is times 0.0000, and I'll go ahead and write down 4 significant digits. 4, 3, let's see, what is it? 4343, because I would round this one up because of the 7 next to it. So I'll round the 2 up and I get 0.00004343. The decimal was right here and it moved 5 places in a negative direction. 1, 2, 3, 4, 5. That's what that -5 means up there. So that's what this number is. Now, all I really want to do is to get this, isolate this term that has my t in it. So I'm going to divide both sides, right? I'm going to divide both sides by 0.00004343. And I know these are not fun numbers, but when we're dealing with finances like this is quite often what we have. So I'm going to say 0.3617 divided by 0.00004343, and just be really careful and check that you've got it written right. And what I ended up with is 365t is equal to 8,328, and I'll just go to 2 decimals here, 0.34. And now all I have to do is divide both sides by 365. Because this was basically giving it to me in days, time in days, and I want time in years. I'll divide it by 365, so I'll say answer divided by 365, and I end up with time is equal to, and let's round it to, it was 22.8. Let's go to the nearest year, 23 years. So time is, this one's going to be 23. So what we basically are showing is that even with these really complicated formulas that we have for finding interest, that we can, if we don't know the rate or we don't know the time or we don't know one of these factors that's up here inside our formula, that's up here in the exponent, now we know how to solve for that.